Vector calculus. They're up to lecture 10. So that may remind you that the first midterm exam, there are two, will be a week from today, Monday, March 11, in Gillette Hall. I'll have to post the room number. In person, you have to be there. During regular class time, 11 o'clock, 12:40, 7 o'clock a.m., 12:40 p.m. And I will distribute or post on Blackboard practice exam. So the one thing you know for sure is that none of the questions on the practice exam will be on the real exam, but it gives you some idea of the format. And I hope I will do that today and go over it on Wednesday. So the exam covers everything we've done from the start of the semester. Some things are more important than others. Everything that we've done having to do with vectors is the key to the course. What I'm not going to, and I might ask you to write a certain point in space in rectangular coordinates or spherical coordinates or cylindrical coordinates, but you're not going to have to graph anything. That's way too hard generally. And those complicated surfaces that are that you find in tables in the books, I certainly don't expect you to memorize and know, and I'm not going to ask about that. So there'll be a minimal amount on cylindrical and spherical coordinates. There probably will be something though. But the most important topics are, most important. So you have to know about vectors, how to add them, scalar multiplication. You have to know what is the dot product, what is the cross product of vectors. You have to know if you're given a vector u and a vector v, how to find the component of v in the direction u. And you have to know how to find the angle between vectors. So component of v in direction u, and the angle or the cosine of the angle between two non-zero vectors. And you also have to know certainly about equations of lines and planes in space. So for equations of lines, for example, you have to know how to describe parametric equations of a line. And you have to know the normal vector to a plane. You have a plane, it's generally described as you have a point on the plane and a vector perpendicular or normal to the plane. And the plane consists of all vectors, all points Q, where the vector from P to Q is perpendicular to this normal vector. So this is all stuff that we did at the very beginning, the first part of the course, and it's very important. You can't do vector calculus without knowing vectors. But then the more important part, and certainly half the exam at least, are vector valued functions. So you have a function r of t in space, which has coordinate functions x of t, y of t, z of t. So this is one way to write a vector valued function in terms of the unit vectors I, j, and k, or it's just in terms of its coordinates x of t, y of t, z of t. So these are exactly the same thing, just two equivalent way of writing a vector valued function. So this is all in chapter 14, and I want to go over some of the homework problems in chapter 14. That's a good review. So maybe some problems that aren't necessarily homework problems. So this is in section 14.2. If anyone has a question from the homework or any other question from this section, I'm happy to do it right now. Otherwise, I'll just pick some problems at random. So for example, problem 13, we have the vector value function r of t, which is e to the ti plus 2 e to the minus tj minus 4 e to the 2tk. So let's recall, if your vector valued function is given like this, then r of t is differentiable if the three coordinate functions, x of t, y of t, z of t, are differentiable. And the derivative of r of t, r prime of t, you just differentiate each coordinate separately. So in this case, x of t is e to the t, so x prime of t is e to the t. Y of t is 2e to the t. Oops, this is a minus sign, 2e to the minus t. Y of t is 2e to the minus t. The y prime of t is minus 2e to the minus t. And z of t is minus 4e to the 2t. So z prime of t is minus 8e to the 2t. So for this vector valued function r of t, the derivative is what you get by differentiating term by term, e to the ti minus 2e to the minus tj minus 8e to the 2tk. That's the derivative. Any questions about that? Number 16, r of t is the vector valued function t plus 1 to the minus 1, inverse tangent of t, log t plus 1. And you can't do vector calculus if you don't know calculus. So you certainly have to be able to differentiate these functions. The derivative of t plus 1 to the minus 1 is minus t plus 1 to the minus 2. The derivative of the inverse tangent of t is 1 over the square root t squared plus 1. And the derivative of the log of t plus 1 is 1 over t plus 1. Any questions about this? So you think of r of t as one way to think of it is it's the path of a particle moving in space. R of t is the position of the particle at time t. So in space, you can think of particle tracing out some curve, just moving in space. You think of often as t as time. So this is the position at time t. And just as for an ordinary curve in calculus, at any point on the curve, there's a tangent line. At any point on a curve or a trajectory in space, you have a tangent vector. And the tangent vector is simply the derivative of the vector valued function at any given point. So if you have r of t equal x of ti plus y of tj plus z of tk, here's your r of t, and at any point on this curve, there's a tangent vector, which is just by definition r prime of t. So the tangent vector at t, it only exists if the derivative is different from 0. It's the vector r prime of t if r prime of t is not the 0 vector. If it is the 0 vector, you don't have a tangent vector. So for example, if we take r of t equal to t cosine 2t 2 sine t, and we want to find the tangent vector at t equal to pi over 2. Well, if this is r of t, then the derivative r prime of t is the derivative of t is 1. Derivative of cosine 2t is minus 2 sine 2t. And the derivative of 2 sine t is 2 cosine t. So r prime at time pi over 2 is 1 minus 2 times the sine of 2 times pi over 2 is pi, 2 times the cosine of pi over 2. That's 1. Sine of pi is 0. Cosine of 2 pi is 0. So the tangent vector at t equal pi over 2 is just the vector 1, 0, 0, which is the vector we call I. If the derivative of r of t is not 0, then the unit tangent vector is capital T of t. It's just a unit vector pointing in the same direction as the tangent vector. So that's r prime of t divided by the length of r prime of t. So for example, in number 24, if r of t is cosine t sine t 2 for t between 0 and 2 pi, the derivative r prime of t is minus sine t cosine t 0. The length of r prime of t is the square root of minus sine t squared plus cosine t squared plus 0 squared. This is just sine squared plus cosine squared, which is 1. Square root of 1 is 1. This is 1. So this is already a unit vector. So the unit tangent vector in this case is just equal to the tangent vector. That's pretty simple. So these are still problems in section 14.3. Suppose we have r of t, this is number 28. R of t is the vector valued function e to the 2t, 2e to the 2t, 2e to the minus 3t. And we want to find the unit tangent vectors at any t greater than or equal to 0. So for this vector valued function, the tangent vector, the derivative, is 2e to the 2t, 4e to the 2t, minus 6 e to the minus 3t, which is not 0. What is the length of this vector? Well, the length squared is the sum of the squares of the coordinates. 2e to the 2t squared plus 4e to the 2t squared plus minus 6e to the minus 3t squared. This is 4e to the 4t plus 16e to the 4t minus 36 e to the minus 6t. This is 20 e to the 4t. Oh, this is plus 36 e to the 6t. So the length of the tangent vector is the square root of this. If I want, I could factor out e to the 4t. This is e to the 4t. Actually, even I can factor out 4e to the 4t times 5 plus 9 e to the 2t. 4 times 5 is 20. 4 times 9 is 36. So this is 2e to the 2t times the square root of 5 plus 9e to the 2t. So if I take r prime of t and divide by its length, that's 1 over 2e to the 2t square root of 5 plus 9e to the 2t times 2e to the 2t, 4e to the 2t, minus 6e to the minus 3t. So this is 1 over 2e to the 2t, square root of 5 plus 9e to the 2t. From this vector, I could factor out a 2e to the 2t, I would get 1, 2, minus 3 e to the minus 5t, I think, because this times this is 2e to the 2t. This times this is 4e to the 2t. This times this is minus 6 e to the minus 3t. These cancel. So I get 1 over the square root of 5 plus 9 e to the 2t. 2 over the square root of 5 plus 9 e to the 2t. And minus 3 e to the minus 5t over square root of 5 plus 9 e to the 2t. So if I were lucky and managed to do this right, that's the answer. I always like to double check what I did. So let me just look at it for another second. Maybe just to check one thing, I'll see if I can check whether or not this really is a vector of unit length. So this is supposed to be the unit tangent vector t of t. So if I take this vector, I want the length squared. So I just take the sum of the squares of the coordinates. That's 1 over 5 plus 9 e to the 2t plus 4 over 5 plus 9 e to the 2t. If I square this, I get 9 e to the minus 10t over 5 plus 9 e to the 2t. So when I add up, the denominator is 5 plus 9 e to the 2t, and the numerator is 5 plus 9 e to the minus 10t. So it's almost correct, but something is wrong. I'm actually happy when I get something wrong because then I get to go back and check. So let me see what I did wrong. So r of t is e to the 2t, 2e to the 2t, 2e to the minus 3t. So the derivative is 2e to the 2t, 4e to the 2t, minus 6e to the minus 3t. The length of this squared is 4e to the 4t, 16e to the 4t, 36e to the minus 6t, which is 20e to the 4t plus 36, e to the minus 6t. There's a mistake. That's the square. So if I take the square root, I get the length. So if I factor out 4e to the 4t, this is 5 plus 9e to the minus 10t. It should be minus 10. So this divided by the length this is minus 10. 2e to the 2t. Oh, sorry. 2e to the 2t. R prime. 4e to the 2t minus 6. No, this is right. Minus 6e to the minus 3t. Divided by 2e to the 2t plus 9e to the minus 10t. So this should be minus 10. So if I factor out 2e to the 2t from this, I get 1, 2 minus 3e to the minus 5t. If I divide by 2e to the 2t, I get 1, 2 minus 3 e to the minus 5t, but this is minus 10 here. So when I checked, this is minus 10, minus 10, minus 10, and now it's perfect, and I get 1. So checking your work is always a good thing to do. Any questions about this? So you have to know how to compute the derivative of a vector valued function, how to find the unit tangent vector, and it's good to know how to check to get things right. Definite integrals. If r of t is x of t I plus y of t j plus z of t k, then the integral from a to b of r of t dt you get by integrating each coordinate function. The integral from a to b x of t dt I plus the integral from a to b y of t dt j plus the integral from a to b z of t dt k. So if we have, for example, this is number 73, which is one of the homeworks, the integral from 0 to the log 2 of e to the ti plus e to the t cosine pi e to the t j dt. This is a vector valued function in the plane. There are only 2 coordinates. So you have to know how to integrate these coordinates separately. So the integral of e to the t dt from 0 to log 2, the integral of e to the t is e to the t evaluated from 0 to log 2. E to the log 2 is 2, e to the 0 is 1. So this first integral will give you 1. Second integral looks a little harder. You have the integral of e to the t cosine of pi e to the t dt from 0 to log 2. But if we make this substitution, u equal to pi e to the t, so du is pi e to the t dt. This is the integral. I have cosine of pi e to the t, which is u, e to the t dt, which is 1 over pi du. And when t is 0, u is pi. When t is log 2, u is 2 pi. So this is the integral of cosine u from 0 to 2 pi. The integral of the cosine is the sine of u from pi to 2 pi. Sine 2 pi and sine pi are 0, so this is 0. So we get that this integral is just equal to I. That's the answer. We should also know how to do indefinite integrals. These were definite integrals, integrals from A to B. So for example, number 59, we have the vector value function R of t equal t fourth minus 3t, 2t minus 1, and 10. So the indefinite integral of R of t dt, you integrate each coordinate separately. That's the integral of t to the fourth minus 3t dt, integral of 2t minus 1 dt, integral of 10 dt. So the integral of t to the fourth minus 3t is 1/5 t to the fifth minus 3/2 t squared plus an arbitrary constant. Integral of 2t minus 1 is t squared minus t plus a constant. Integral of 10 is 10t plus a constant. So this is 1/5 t to the fifth minus 3/2 t squared, comma, t squared minus t, comma, 10t, plus the vector of constant c1, c2, c3, which I can just call a vector c. So the indefinite integral of this function is this, plus an arbitrary vector constant or constant vector. Any questions about any of these? Let's look at number 65. We have r prime of t is, so this is the tangent vector, the derivative of some vector valued function is e to the t sine t secant squared t. And we want to find from the derivative of the vector valued function, we want to find the original function with the initial condition that r at time 0 is 2, 2, 2. So what does this mean? If r of t is x of t, y of t, z of t, then for example, x prime of t is e to the t, which means x of t is e to the t plus a constant when you integrate. Y of t, y prime of t, is sine t, which means when you integrate y of t, that's the integral of sine t dt, is minus the cosine t plus a constant. And z prime of t, when you differentiate it, is secant squared t. So z of t is the integral of secant squared t dt, which is the tangent of t plus a constant. So r of t is e to the t minus cosine t tangent t plus some constant vector. And we just have to satisfy the initial condition at time 0 is 2, 2, 2. So r at time 0 is e to the 0 minus cosine 0, tangent of 0. E to the 0 is 1. All right. E to the 0, all right, plus c. E to the 0 is 1. Cosine 0 is 1, so minus cosine 0 is minus 1. Tangent 0 is 0. So 1 minus 1, 0 plus c is equal to 2, 2, 2, which means c has to be 1, 3, 2. So that tells us what r of t is. So if you want to write it down exactly, r of t is e to the t plus 1 minus cosine t plus 3, or 3 minus cosine t, tangent t plus 2. So this is the answer. Okay. Any questions about these? Yeah, let's do one more. So let's just remember what's going on. We have r of t. This is our vector valued function. At any point on this curve, the tangent vector, this is the curve. And then we have r prime of t is the tangent vector. And there is a tangent line. So the tangent line is the line at t is the line passing through this point in the direction of the tangent vector. So this red is the tangent line. And how can we actually impute that? So this is number 81. Suppose we let r of t be 2 plus cosine t, 3 plus sine of 2t, t, and we want to find the equation of the tangent line to the curve in the direction of the tangent vector at the time t naught equals pi over 2. So this is my vector valued function r of t. At any point t, r prime of t is equal to the derivative. The derivative of 2 plus cosine t is minus sine t. The derivative of 3 plus sine 2t is 2 cosine 2t, and the derivative of t is 1. So at time pi over 2, r at t naught, that's r evaluated when at the time pi over 2, is 2 plus cosine pi over 2, 3 plus the sine of 2 times pi over 2, pi over 2. Cosine of pi over 2 is 0, so 2 plus 0 is 2. Sine of pi is 0, so this is 3. And pi over 2 is pi over 2. So the point on this curve, r at time t naught, is 2, 3 pi over 2. The tangent vector at t naught, or the tangent vector at the time pi over 2, is minus the sine of pi over 2, 2 times the cosine of 2 times pi over 2, and 1. Sine of pi over 2 is 1, so this is minus 1. 2 over 2 cancel. Cosine of pi is minus 1, so this is minus 2 plus 1. So we want to find the line through 2, 3 pi over 2 in the direction minus 1, minus 2, 1. So this line, the parametric equations are 2 minus t, 3 minus 2t, pi over 2 plus t. These are the parametric equations for the line. So everyone can see. Any questions about this? Let's look at some of the homework, which is due on Friday. So section 14.3 is on motion. Motion in space. So r of t is the position of a particle at time t. R prime of t is the velocity. It's a vector, velocity at time t. The length of the velocity vector is the speed of the particle. So velocity has a direction. The magnitude of the velocity is called the speed. And the second derivative, r double prime of t, is acceleration. So one of the simplest kinds of motion is circular motion in two-dimensional space in the plane. So you have a particle going round and around a circle of radius a. So one way to write this, and let's say at time 0, it's right here on the x-axis. R of t is A cosine t, A sine t. So at any time t, the length of this vector is the square root of the sum of the squares of the coordinates. That's the square root of a squared cosine squared t plus a squared sine squared t. So I can factor out the a squared. This is 1. So this is the square root of a squared, which is the absolute value of a. And if a is positive, you're just moving around the circle in this direction. What is the velocity? V of t is the derivative. The derivative of this function is minus a sine t, a cosine t. What is the direction of this? If we take the dot product of r of t and r prime of t, that's the dot product of the vectors a cosine t, a sine t, dot product with minus a sine t, a cosine t. When you take the dot product, you multiply the coordinates and add, so you get minus a squared cosine t sine t plus a squared cosine t sine t. That's equal to 0. So the dot product equals 0. But the dot product, r prime of t, dot product with r prime of t, is also the length of the two vectors, the product of the lengths of these vectors, times the cosine of the angle between them. Now, the length of each of these vectors is a. This is a and this is a. So this is a squared cosine theta, which is 0, which means theta is pi over 2. So the angle between these two vectors is pi over 2. That means r of t and the velocity v of t are perpendicular to each other. So at any given time, if this is r of t, perpendicular to it is the velocity. So in circular motion, the velocity is perpendicular to the radius vector. What about the acceleration? That's the derivative of the velocity. This is the velocity. If you differentiate this, you get minus a cosine t minus a sine t. This is minus a cosine t, a sine t. But this was just r of t. This is minus r of t. So the acceleration has the same magnitude as the position, but it's pointed in the opposite direction. So if this is the radius vector, then the acceleration vector is the same length, but pointing back towards the center of the circle. So that is a nice fact about circular motion. Now, the basic example of vector calculus has to do with, and the simplest is two-dimensional. So two-dimensional motion in a gravitational field. So Newton's second law says if you have a particle moving, the sum of all the forces on the particle is, how does it make the particle move? It's the mass times the acceleration. So the acceleration of the particle, which tells you where the particle is going and how fast and in what direction, is the sum of all the forces. So in vector notation, if you had a lot of forces and you add them all up, this is equal to the mass times the acceleration, or the mass times the second derivative of the particle. And the simplest example is when the only force is due to gravity, and the force due to gravity is minus mg. G is the acceleration due to gravity, which is, depending on your units, 32 feet per second squared, or 9.8 meters per second squared. So when you have a force, sorry, I should write this as a vector. So the force, it's in the y direction going down, 0 minus g. So mass times acceleration is the force, when you have the force of gravity, is 0 minus mg. And you can cancel the m's. The acceleration is 0 minus g. So if the only force acting on a particle is gravity pulling it down, the acceleration anytime near the surface of the Earth is constant, and it's 0 minus g. So from the acceleration, I want to get the velocity, and from the velocity, I want to get the position. So let's suppose that you have an initial condition, an initial position, and an initial velocity. So let's say the initial velocity at t equals 0 has coordinates, it's v of 0 equals, say, u0, v0. And the initial position at t equals 0, that's the position r of 0 times 0 is x naught, y naught. So the acceleration, which is 0 minus g, is the derivative of the velocity. Which means, if you look at it, means that the velocity, when you differentiate its x component, you get 0. So this is just some constant, u0. And when you differentiate the y component, you get minus g. So this is minus gt plus v0. So if the initial velocity is u0, v0, then the velocity at time t is given by this formula. But then r of t, or what's it? Then, so the velocity is the derivative of the position. So when you differentiate the first coordinate x of t of the position, x of t, x prime of t is u0. So x of t is u0t plus x0. And When you differentiate y, you get minus gt. So that means when you integrate this, you get minus a half gt squared plus v0 t plus the initial y naught. So if you have something which is moving only under the force of gravity, so the acceleration is just the acceleration on the particle coming from gravity, if it starts at position x naught, y naught, and has an initial velocity u naught, v naught, then this formula, which is certainly highlighted in the text, this is on page 888, that tells you where your particle is. So let's look at some examples. The more one does of these examples, the better, because it's certainly important for us. So this is example 4. In section 14.3. So a baseball is hit, and the bat makes contact with the ball 3 feet above home plate. With initial velocity in feet per second, v of 0, u naught, v naught, 80, 80. So that the x component and the y component of its initial velocity, that is when it comes off the bat, is 80 feet per second. Find the position and velocity of the ball from the time it is hit until it hits the ground. So you start 3 feet up, and the ball is hit, and it has some initial velocity like this, and it's going to move, and at some point it's going to hit the ground, and you want to know, as a function of time, t, what is r of t, what is its position, and what is its velocity? So our formulas for position and velocity are the following. V of t is x prime of t, y prime of t. This is u0 minus gt plus v0. In this case, u0, the initial velocity in the x direction is 80, and the initial velocity in the y direction is 80. So this is 80. What is g? G is 32 feet per second squared. So this is minus 32t plus the initial velocity in the y direction, 80. And what is the position at time t? R at time t is u naught t plus x naught minus a half g0 t squared plus v0 t plus y naught. What is this? u0 is the initial velocity, 80t. x0 is the x component when you start, that's at 0. you're starting at the point 0, 3. So x0 is 0 and y0 is 3. Minus a half g, acceleration due to gravity, is 32. So minus a half 32 is minus 16t squared plus v naught 80t plus 3. So 80t minus 16t squared plus 80t plus 3. This is the position at time t for all t greater than or equal to 0. And the derivative, again, is 80 minus 32t plus 80. So for this particle, for this baseball, at any time t, x of t is 80t, and y of t is minus 16t squared plus 80t plus 3. Suppose we want a curve to express the trajectory of the ball. So we expect it to actually be a parabolic arc, and let's solve for y in terms of t. So y is minus 16t squared. So if x is 80t, then this is what? This is the y is minus 4t squared plus 80t plus 3. So 80t is x. So if I divide by 20, x over 20 is 4t. So this is minus x over 20 squared plus 80t, which is x, plus 3. So this is minus x squared over 400 plus x plus 3. So this is y as a function of x. If you graph y as a function of x, this is a parabola. It's a quadratic equation with a negative coefficient opening down. What is the maximum height the ball gets to? So the height at time t, well, we can do it in either of two ways. If we use from this equation, y is minus x squared over 400 plus x plus 3. So dy dx, if I differentiate, is derivative of x squared is 2. I get minus x over 200 plus 1. And when is this at its maximum? This is equal to 0 when x equals 200. And when x equals 200, what is y? Y is minus 200 squared over 400 plus 200 plus 3. So this is minus 200 over 2, or minus 100 plus 200 plus 3. That's 103. So the maximum height the baseball reaches is 103. And when does it hit the ground? It hits the ground when y is equal to 0. And how far is it when it hits the ground? So when y is 0, you get 0 is minus x squared over 400 plus x plus 3. So you have to solve this quadratic equation. X squared minus 400x minus 1200 equals 0. I think that's if you rearrange it. you get this quadratic equation. And what is the solution of that? This is the same as x minus 60 x plus 20. Is that right? X squared minus 1200. No, that's not right. This is not what they're asking, but let me continue to solve this. So we start hitting the baseball 3 feet above the ground, and it goes in a kind of an arc like this. And the position at time t, the parametric equations that we worked out, where r of t is 80t minus 16t squared plus 80t plus 3. So this is x of t, and this is y of t. And when we solve for y in terms of x, we get y is minus x squared over 400 plus x plus 3. So if we're looking at this as a function of this is x and this is y, when x is 0, you're at 3. And at any point x, this is what this parabolic arc looks like. That's the parabola. Okay. When does the ball, assuming a flat playing field, how far does the ball, so assuming that there's no fence anywhere, where does the ball hit the ground? So the baseball hits the ground when y is 0. That means minus x squared over 400 plus x plus 3 equals 0. So you're solving the quadratic equation, x squared minus 400x minus 1200 equals 0. And there's no, this equation doesn't factor. I hoped it would. So by the quadratic formula, x is equal to minus b plus or minus the square root of b squared minus 4ac over 2, which is 200 plus or minus a half square root of 400 squared plus 4,800. This is the same as 400 times 12. So this is 200 plus or minus 1/2 the square root of 400, which is 20 squared times 13. Square root of 20 squared is 20. Half of 20 is 10. I get 200 plus or minus 10 root 13. Let's see. Root 13 is between 3 and 4. This is between 30 and 40. Hmm. So I don't have a calculator here, so I can't do that. But you can also look at y of t. Y of t is minus 16t squared plus 80t plus 3. The height is equal to 0 for what value of t? So you have to solve this quadratic equation for t squared. That's the same as t squared minus 5t minus 3 over 16 equals 0. Anyway, solve for t, plug into x of t, and you get your answer. That's really the whole thing. Any questions about this? I mean, the hard thing is setting it up. Once it's set up, then you just need a calculator because you can't solve these equations by hand effectively. Okay. Let's look at a little bit of the final section that we're covering, which is 14.4. So there's basically one thing to learn in this section, which is how to find, or what is the formula for, the length of a curve. So 14.4 is length of curves. So if you have a curve, r of t, given parametrically by, we'll use f, g, and h in this case, f of t, g of t, and h of t. The length of the curve for t going from A to B. So you have r of t. Here it is at time A. Here it is at time B. And you want to know how long is that curve? What is the length of that curve? So the length, L, is given by the following formula. It's the integral from A to B of the square root of f prime of t squared plus g prime of t squared plus h prime of t squared dt. Of course, if r of t is given parametrically in this way, then the tangent vector r prime of t is f prime of t, g prime of t, h prime of t. That's just the derivative. So the length of the tangent vector is the square root of the sum of the squares of the coordinates. That's exactly what we have here. So another expression for the length of a curve from A to B is you integrate the speed dt. So let's look at a couple of the homework problems from this section. Problem number 13 is to find the length of the following curve. R of t is cosine t plus t sine t, and comma sine t minus t cosine t. So this is a curve in the plane. It's in 2 dimensions. And I want to find the length of this curve for t going from 0 to pi over 2. So r prime of t, the derivative, if you differentiate this, you get minus sine t plus sine t plus t cosine t, comma, cosine t minus cosine t plus t sine t. These cancel. So you get t cosine t, t sine t. So if this is r prime of t, then the length of this vector, r prime of t, it's the square root t squared cosine squared t plus t squared sine squared t. This is 1, square root of t squared is t. This is just t. So the length of the curve, L, is the integral from 0 to pi over 2, length of r prime of t dt, the integral from 0 to pi over 2, t dt. The integral of t is a half t squared from 0 to pi over 2. That's a half pi over 2 squared. That's pi squared over 8. So that's the answer. 14.4, number 13. Pi squared over 8. Good. Let's look at number 17. We have a curve r of t given parametrically by t, 8 sine t, 8 cosine t, t going from 0 to 4 pi. If you differentiate this, you get 1, 8 cosine t minus 8 sine t. The length of this vector is the square root of 1 plus 8 cosine t squared plus minus 8 sine t squared. This is square root of 1 plus 8 squared, that's 64, times cosine squared t plus 64 sine squared t. Factor out the 64, but cosine squared plus sine squared is 1, so we get the square root of 65. So our integral from 0, this is the length, this is the integral from 0 to 4 pi of root 65 dt is just 4 times root 65 pi. And that's the answer. Let's do a couple more. Number 23. We have a particle moving, and its position at time t is 2t cubed minus t cubed, 5t cubed. And we want to find its speed at any given time and the length of its trajectory for t going from time 0 to time 4. So if this is r of t, r prime of t is derivative of t cubed is 3t squared, so you get 6t squared minus 3t squared, 15t squared. So the length of this vector, the speed, is square root of 6t squared plus minus 3, 6t squared squared minus 3t squared squared, 15t squared squared. So that's the square root of, so I have t to the 4th in every one of these terms, and then I have 6 squared is 36, 3 squared is 9, 15 squared is 225. So 13 and 36 and 9 is 45. 45 and 25, 225 is 270. So this, and square root of t fourth is, this is t squared times the square root of 270, or this is the same as 9 times 30. I could say 3 root 30 t squared. So if I've done my arithmetic okay so far, 3t squared root 30 is the speed. And the length, so this particle is moving from time 0 to times 4, and the length of the arc is the integral from 0 to 4 of 3 root 30 t squared dt. That's 3 root 30. The integral of t squared is 1/3 t cubed from 0 to 4. The 3's cancel. T cubed is 64. Cubed is 64. So I get 64 root 30. Right. Any questions about any of these? These are sort of straightforward problems of the sort that you can expect to show up on the exam. And, you just need to demonstrate a basic understanding of what we've covered so far in vector calculus. Again, I remind you, they're going to be office hours, Zoom, not office hours, but Zoom problem sessions. I think maybe Tuesday, Wednesday, Thursday at 7 p.m., as well as Friday afternoon at 4:30. And I encourage you to log on and ask questions. And we'll also do review on Wednesday morning. Any questions before we quit for the morning? All right. Supposed to be a beautiful day, so I hope everyone gets to enjoy it. And see you on Wednesday.
Thank you. You too, sir. Have a good one.
Thank you.
Have a good one, Professor.
Someone asked if you can have more time for the homework. Yeah, you can turn the homework in late. It's more important to me that you do the homework.